you have it's a vector valued modular form on the vector space with basis simple objects, and now you take a basis vector corresponding to a simple object, and what it means is the action of S of the SL2Z S is given by an element in this vector space, and it is given by this formula. A very good question. So, and here B goes now over this basis, which are the irreducible objects in the category. All right, and similarly, the action of T is just given by the scalar with which a theta acts on A. So I just write it like this, that the T is diagonal in this basis. All right, and now it's a good good question, and please remember this formula until the end of this.
It's not possible to read it from here, sorry, with this pen.
The pen is still not good, yeah. Yeah, I just, I want to end. No, I don't. So let me just write it here as well. But the pen is not good at all, right? Yeah, it should say T, yeah. Yeah, okay, let me, yeah, this is much better. Yeah, good. So the question was, what did I exactly mean that the Hopf-link is the S matrix, gives the S transformation? What you do is you take a vector space that is just given by the linear span of irreducible objects, and then the S transformation maps a basis vector to this linear combination, coefficients given by the Hopf-links. Okay, very good. So the morning was a review about various tensor categories, with the main thing I wanted to point out is that these fusion rules, as long as you have a braided tensor category that allows for a trace that has duality, then you can express the fusion rules, the multiplicity of tensor products, in terms of using the Hopf-links, in particular using the closed Hopf-link in the semi-simple setting. Okay, now now the question is what does VOA know? And I will write down I will write down the main theorem. So if you look at VOA literature and tensor categories, people always say there exists a vertex. I mean, we are looking, or we are interested in a vertex tensor category in the sense of HLZ. And in now roughly 15 years ago, they have written a series of 8 papers, each more than 50 pages, where the main point of this whole collection was to work out, to establish a theory of braided tensor categories for vertex algebras. And let me give you this statement. So we are interested in a VOA and a category of modules for it. And now we.
So again, when you say separated, does it mean that zero eigenvalues are integers, or just
for the VOA itself, yes. Okay. And for yeah. Okay, So what do we want to? We have these intertwining operators, and we now want that there exists exactly like in a tensor product of vector spaces. Tensor product of vector spaces is defined by a universal property. So what is the tensor product of two VOA modules? It is given by a universal intertwining operator whose target is a certain module, which that module we denote by the tensor product, such that any intertwining operator of type module number 1 times module number 2 to something has to factor through this universal one. So for any two modules, so I now drop writing objects and see. So for any, there exists an object denoted by M box N. So that's what we will then call the tensor product of M and N, together with something we will call the universal intertwining operator of type Mn. So it's an intertwining operator of type M and N to this big object, potentially big object M box times N, such that the universal property is satisfied. This means for any other object and corresponding intertwining operator of this type we have a morphism of VOA modules to R, such that the diagram that you can write down commutes. The universal property that you usually require. Okay, and the second condition is the associativity condition that you need to require.
Just to make sure I understand. Inside this F, does that F have the Z and log Z in it, or does it somehow not have any Z's and logs in it?
That doesn't have any Z's and logs in it. It's just, I mean, here so here we have a, here we have a homomorphism of VOA modules. So that's in particular a homomorphism of the underlying vector spaces and the vertex operators, and it induces an homomorphism on the corresponding formal power series. In particular, the F here has no Z in it. Okay, so the associativity property, this will take a while to state. For any triple of objects and complex variables Z1 and Z2, there is a natural family of isomorphisms which are labeled by these complex variables. And eventually the associator wants to be a certain limit of this family of families. So we have a family of isomorphisms labeled by two complex parameters. And how is this related? Well, so we require that in the region Z1 larger Z2 larger Z1 minus Z2, we have two expressions. We have our we can take the product of two intertwining operators. So lowercase m, n, and r are vectors on the modules m, n, and r. So we can act on this one. This here is then an intertwining operator of type n, r to n times r, so that we can act on the answer with this one to get an intertwining operator of type m and n times r to m times n times r. So to here. And the other expression that we have is is the pen still readable? Not really, right? So you again should compare this expression to what we had in the duality. It's, and it was exactly the type of statement I was always saying is of associativity type. Right, here we first apply the intertwining operator of type m and n to m times n inside the argument, so that and now with the answer we act on r with an intertwining operator of type m times n and r to m times n to r. So this means the answer is in here. And the requirement is that these two expressions converge absolutely. For any choice of branch of logarithm. For the two variables. And where do they converge? These are not in these vector spaces, but they are algebraic completions, just because these are infinite sums. So the first one converges in the algebraic completion of this module here. So algebraic completion you usually denote with this bar over the module, and the second expression you have your brackets the other way around. respectively. So this it's in the algebraic completion. Well, what you allow here in the algebraic decomposition is you allow for infinite direct sums. So this is a vector space that is naturally integer graded, and so we can have here linear combinations of infinite linear combinations, but in each graded the component in each the projection on each graded component has to make sense. So what it is, it's this module is integer graded, and it's the direct product of the graded components. So and now what do we want this alpha? So we want these two expressions to converge, and this alpha is defined as follows. So I have to start erasing here. So we have one condition is the universal property of the intertwining operator, and the second condition is an associativity property, which I'm stating at the moment. So and now the alpha has to come into the game. So and we want that alpha bar of Z1 and Z2 on the first expression that I wrote down. You know, let me write save some writing and call this just expression number 1, and this expression number 2.
Yesterday you imposed your convergence conditions by taking matrix coefficient. Is that essentially the same as saying that the thing itself converges in completion?
Can you say it again?
I'm trying to understand the difference between the kind of convergence condition you asked for yesterday and the one you asked for today. So yesterday...
Yes, the matrix coefficients, they select the coefficients. So yes, that's a good point.
It's basically the same kind of convergence.
It is the same time, absolutely. Absolutely, and in particular, you could the convergence you could now also have phrased in terms of matrix coefficients, and that would be a way to do that. You're totally right. So we want. I hope it's okay that I don't copy this lengthy expressions again. So we want that the first expression, which is in here, if I apply alpha bar to it, I get this one. And what do I mean by alpha bar? The natural extension of this one to its algebraic completion. Where this one here is the natural extension to the completion, to the algebraic completion. Okay. So the statement is if condition 1, this universal property of intertwining operators, and condition 2, associativity in this sense here, holds, then the category C, so this category of VOA modules, C is a braided tensor category.
Everything until now was a hypothesis.
Everything until now was a hypothesis, absolutely. And it tells you exactly the difficulty, right? The difficulty will be to understand whether in a given category hypothesis number 2 is satisfied, whether I can somehow analytically continue expressions of type number 1 to expressions of type number 2, or not analytic, whether they are related, their continuations are, they are somehow related. So So the difficulty of getting a tensor category is the difficulty to make sure, the problem to make sure that this condition holds. Yeah. And if we have so it's a tensor caddy, and now what's the structural data of this tensor caddy? So let me give you a list. Right, we introduced this morning. A braided tensor caddy has a unit object. It has a commutator. It has an associator. It has a left multiplication by the identity. It has a right multiplication. It has a ribbon twist, and so on. Well, okay, for ribbon twist you need ribbon structure. We don't necessarily have this, but we'll always have something that will be called a twist. And the reason for it will be clear in the statement. So, such that we have unit isomorphisms. That means we have, so the unit is the VOA, and we have a left multiplication on a given module. We have a right multiplication given on a module by the unit. And we always explain what this is on the fields, in this case, on the VOA action on the module. Right. So here we have something in our module, and the VOA is acting on it via the fields. And this, how can we define it? Well, we define it by the module action. For the right multiplication, we now have to swap the order of module and VOA, and it turns out it is given by the formula e to the z L negative 1 acting on the module map of the VOA. Your variable is replaced by negative z and an m. So this, if you compare this to this isomorphism, I had at some point stated that an intertwining operator of type mn and nm are related exactly by taking one intertwining operator, multiplying it by in one direction, multiplying it by e to the z L minus 1. Then I also have here something that in this case disappeared, but also z was replaced by negative z. More generally, it was replaced by e to a choice of minus 1, which we don't need here because it's the module action. The next one is the braiding. So what do we do is here we take an intertwining operator of type, the universal one of type mn. And it's defined to be an e to the z L negative 1 again.
In this unit business, are you saying that the vertex algebra itself is the unit? Is that what's being said?
Yeah. Mm-hmm. Yeah. Unit isomorphism with the property that the tensor unit is the vertex algebra itself. Yes, that's what I'm saying.
Y sub Vm is nothing other than the usual original y.
It's the usual original y, exactly. Right. So this the unit is the left unit is nothing deep. However, for the right unit, you already need here to swap. Okay, now I presented a computation that I really liked because I computed, I prepared one. I computed exactly this swapping for the for the intertwiners of Fock modules using the delta operator, because in that case one really nicely sees if I compare compare this action with this one, I don't get any nice correspondence, but if I multiply it with the e to the z L negative 1, then I indeed get that these two are just related by a phase, which is e to the pi I times the product of the Fock labels, actually e to the negative pi I, which is exactly the square root of the S matrix S kernel I wrote down yesterday. I really don't have the time to present it, and I think you're more interested in what else I'm going to present. But whoever wants to see the detail, just ask me in a break, or it's a nice computation. Okay? It's and I think I really decided to write lecture notes. So once I do that, I will present a computation that illustrates this braiding enormously. I really like it very nicely in the Fock module case. Okay. Anyway, the braiding is given by this formula, and then you also have something. So a vertex tensor category is very far from being automatically a ribbon category. You expect it, but you have a hard time to prove it. But what it always has is it has something called a twist. And this twist is just defined by the action of e to the 2 pi I L naught on the module M. The module, a simple module will always be integer graded, so this makes sense. But what sometimes will happen is that L naught will not act semi-simple, so sometimes it will just be graded by generalized eigenspaces, and then that would also correspond that this twist is not acting semi-simply. So that's and why do we call it twist? So those who know categories, what does the ribbon twist in a ribbon category satisfy? Anybody? I didn't present that. It satisfies a nice property. Gregor?
Compatibility with tensor product.
Yeah, right. It actually satisfies many nice properties. I probably didn't ask that well enough. I wanted to hear balancing, right? And even though this doesn't need to come from and balancing is the following. The twist on the tensor product is the same thing as the tensor product of the twists times the monodromy. And the monodromy is you braid once and then you braid again. It's the double braiding. Right, so
That's exactly what I would call compatibility.
oh, that's what you meant. Okay, perfect. Then thank you for your answer. In fact, yeah, what else could have been it been?
Right,
yeah. Right. See, if you stand here, you're not capable to think about the answers so much. Yeah, absolutely. So it's compatible with tensor product in the sense, right? Naively, you would maybe have hoped for something like this. Which holds in what kind of category? In a symmetric category where the braiding is trivial in the sense that the monodromy, the double braiding, is trivial, right? And in a general non-symmetric tensor category, braided tensor category, it is compatible in the sense that the tensor product of the twist is the twist of the tensor product up to monodromy. Excellent. And finally, the last thing is associativity. So we have that the associator for 3 modules is given by the associator of the three modules defined before by this natural family, but that was now defined for two complex variables, and we want just a quantity. So what do is we take first the limit z1 minus z2 to 1, and then once we have done this, we take the limit z1 to 1. And we also have to say how we take the limit. So we take it along the real line. Then the positive, non-negative real line. With choice of branch of logarithm
Why is z1 minus z2 to 1 a limit at all? Why is z1 minus z2 to 1 a limit at all? I thought it was just defined as z1 minus z2.
Yeah, I'm actually wondering whether I have a typo here and it should say 0. Let me look this up. I have to look it up. I look it up in the break, okay? Or can anyway.
I'm not sure. Maybe before it was only defined inside of the disk of size 1.
Let me look this up in the break, which we. When do we have it? At 3, right? So quite soon. I'm also confused about this. So with the choice of branch of logarithm, such that the arguments for z1, z2, z1 minus z2 are all 0. Okay, so this took almost a lecture to state.
What is the statement?
The statement is that the associator is this limit, this double limit, where you take this limit in this way. And the statement is that in this theorem we don't only get one natural family of associativity-like morphism, but one for any pair of insertion points. And now we specify our insertion points to get the actual associator. Okay, you can ask me more in the break, maybe. Now, the question is now, does this theorem apply? And for a very long time, until so VUAs came up in the 80s and until maybe the mid-2000s, 2005 or so, the only examples where one could apply the theory, at that time the statement was also stated in less generality and in this way, then were for so-called rational vertex algebras. And now one slowly is improving, so E.G. Huang was then able to remove one adjective in the one very important adjective in the notion of rationality, and then fairly recently we were able to remove a lot. So let me state the conditions under which this theorem applies, and then in practice I said at some point, if you want to do representation theory of vertex algebras, you might like to say you have a list of goals in doing it. And so what you first would like to do is you would like to understand classification results just of modules, right? Classify simples, understand extensions, for example, the classify projective modules, etc. And then ideally you would like to show that you have a tensor category, and then ideally you would study it further. So it means in practice, it means once you are good with the classification, you try to understand whether these finiteness conditions that guarantee the existence of tensor category do hold. And these finiteness conditions, they only have one purpose, namely that condition number 2 in this theorem is satisfied, that somehow you introduce a notion, the obvious notion of matrix elements, you called it, of correlation functions. And you want to understand whether you somehow can do some analytic continuation so that you get your associativity isomorphisms between your different types of correlation functions. Well, how can you understand analytic continuation of those? You want to characterize these correlation functions by differential equations. So you have to get this differential equation somewhere. So the game is, in this setting, is you somehow have to get differential equations. And for example, for Westermino-Witten theories, already in the 80s, people knew that Westermino-Witten theory correlation functions are solutions to Knizhnik-Samolodchikov equations, to very nice differential equations. So there, the situation has always been good. And in general, it turns out finiteness conditions simply guarantee the existence of nice enough differential equations, so the singularity structure is such that you can do your analytic continuation. And these finiteness conditions are called C something finiteness condition. So let me define this and then give you a list of examples of where one has a vertex tensor category structure. So a module is called Cn cofinite. If it has finite, if a certain subspace called Cn has finite codimension in M, so n here is a positive integer, and this Cn subspace is the following subspace. It's the subspace spanned by all vectors in M that you can write of the form you act on a vector in M by the negative n mode of any of any element in V. Okay, let's think about this statement before I continue. I'll make a break quite soon again. We can ask a question. The vertex algebras that we know best are affine vertex algebras, right? And now let's take a lower bounded module. The ones that we introduced were these what I called VK rho. So that means we take our representation of the finite dimensional Lie algebra. We let all positive modes act as 0 and induce. What's the induction given by? It is given by the -1 modes, the -2 modes, the -7 modes, I mean all the negative modes. Right? So this means every vector I can write as a vector on the top level times a monomial in the negative modes. In particular, the leftmost, no matter how I choose my ordering, the leftmost mode will be a negative mode. And every negative mode is the -1 mode is just the the -1 mode of the field X. So now X minus n is up to a scalar the -1 mode of the field corresponding to the vector x minus 1 on the vacuum up to a scalar. So this means for an affine vertex algebra, every vector, every monomial in such a module can be written as a top-level vector times something, which is just a vector on the module, and then a leftmost mode, which is a -1 mode. In other words, the C1 subspace of any module coming from a representation of a finite dimension, of the underlying finite dimensional Lie algebra, has the property that its C1 quotient is exactly the top level. So what can we infer from that? We can infer from this that a module of the affine vertex algebra is C1 cofinite if and only if it's coming from a finite dimensional representation of the Lie algebra. If we go back to SL2 and yesterday, what did I tell you? Almost no representation of interest is finite dimensional. So that's already very bad. Okay, and so it took me forever to find a good. So this finiteness condition will be important, and I still have 3 minutes, and you know I can't afford to lose time. So let me start by stating a few criteria. So it turns out this C1 cofiniteness is key. That's why I was stressing that so much. So a list of theorems. So statement number 1, if M is a C1 cofinite module and N is a C1 cofinite module, it follows that their tensor product is C1 cofinite. So this is a very useful theorem. Let me also give the name, because it's so useful. It's done by Miyamoto.
I didn't understand before. Is there a statement that tensor product always exists? Is that a...
Yes. There's a statement that for C1 cofinite modules, no, there is no such statement, but for C1 cofinite ones there is. And the problem, the intertwining operators, you can define them using co-invariants, but what could and what does happen is that a universal module doesn't exist. So, thank you. For example, Liouville is an example, or it's conjecturally an example at least. If you have all these a generic central charge Virasoro, if you have all these Verma modules, then you expect to run into problems. But that's a complete, yeah. So there are VOAs and representation categories that are just beyond the scope of what the theory is capable of doing at the moment. Okay, let me maybe add one more point of this theorem, and then I will continue with the other points after the break. So now here one takes a VOA that is graded by conformal weight, non-negatively graded. The top level is one-dimensional. These two are often called, a VOA with those two properties is often called a VOA of CFT type, of conformal field theory type. Now, you also require that V is its own contragradient module. And all these three conditions are extremely mild. They almost always hold. They hold very often. But the next one is something that very rarely holds. Namely, the vertex algebra itself is C2 cofinite. So if you look at these conditions, right, of course, the C2 subspace is much smaller than the C1 subspace, and so it is. That means the co-dimension is much larger, and so it is much harder to be C2 cofinite than C1 cofinite. And it turns out C2 cofinite is a very severe condition, and it's so good that you always then get that all V modules form a VTC, a vertex tensor category. A tensor category in the sense I have introduced over the last hour. Okay, and now we will have our break, and then I will quickly tell you what rationality means. It means one more condition here, and I will tell you more things that I do know. And eventually, and I hope I can give you maybe a feeling about why we can still get a tensor category structure on SL2, even though what I will write down has no chance to apply to that. Good. Yeah, let's have a short break.